Hi, I recently completed the Ben Eater SAP-1 Breadboard computer, it was a very fun project. Got to learn a lot of different things about how the innards of a CPU and a computer in general work. But almost as soon as completing it, I wanted to expand it. I wanted to add more functionality and do more complex things with it. Not so much to turn it into some kind of computational workhorse, because you don't build this computer for that, but more to kind of prove to myself that I've learned the various concepts that were being taught in this project. And so one of the first things I realized, in order for me to add more components or modules to this computer, I had to basically expand the control lines. The last thing that you built in the Ben Eater SAP-1 project was to bring it all together and insert control lines. But the implementation in Ben Eater's originally designed only gave you a total of about 16 control lines. And in the end, you ended up using all of them in order to control the overall SAP-1 computer. So if I wanted to add more modules, I have to add more control lines. There are several ways to do this, and I'm going to go into each of them. What are the pros and cons? And kind of cover that in general to make sure and kind of share with you my learnings as to how to do this and what are the issues that you need to work through in order to make it work. So let's get into it. Okay, let me go over the specific design goals that I'm trying to accomplish. First, I want the ability to control the instruction code space and flags used by using EEPROMs with more address lines. The original EEPROMs that Ben Eater used were 28C16s, which had 11 address lines and 8 bits of output. And those 11 address lines ended up, all but one of them were being used. So technically it could expand using more address lines, but I wanted to do more than that. Right now there's only 4-bit instructions, and I know at some point in the future I would like to expand the memory on this machine so that I can have more than just 16 bytes of RAM. And to do that, I need to expand the addressing, and if you expand the addressing, you might as well expand the instruction code space so you can have a richer set of instructions. Furthermore, right now there's only 2 flags in this computer, namely the carry flag and the 0 flag. Adding more address lines would allow you to add more flags if that is desired. Admittedly, I don't have any specific goals around that right now, but I wanted to enable, if I'm going to do all the work to add more control lines, I want to do the work once to enable the ability to expand both the instruction set and flags. My second goal in all of this was that I wanted to expand the number of control lines by at least 2 times. Right now there were 16. I wanted to have at least 32. In the end, I ended up having more than that, and we'll get into the details of that design. But that was a specific design goal. My more immediate projects for expanding this computer do not use all those control lines that I have enabled. But again, if I was going to implement this, I want to implement it once, and so that I could have room to grow as I think of more modules I would like to add to this computer. The third goal is I wanted to make available to the microcode more than just 5 steps that were enabled by Ben Eater's original design. It's not that I wanted to make a lot of steps, but I wanted to make more than just 5. Furthermore, in order to do that, one of the things that you need to implement is allow the microcode itself to reset the step counter once it gets to the end of a particular instruction step. Rather than going through a bunch of 0 or null steps in order to kind of clock out the step counter. This would be for efficiency, and if I was going to add more steps, for sure I needed the ability for the microcode itself to reset the step counter. And finally, and this is kind of just a little nit, it's not really a major goal, but in Ben Eater's original design, the register speeds out control line was not enabled just because he would have needed 17 control lines, and the 2 EEPROMs only afforded him 16. And so, given the instruction set that he implemented, the B registers out wasn't really needed, so he didn't connect it to the control. I'll connect it in this design. Those were my design goals. So let's get into how to actually implement those design goals in a design. Okay, before we get into the design I actually made, let's kind of do a quick review of the important elements of Ben Ader's original design for the control logic. And here you have it, his original design, centered around these two EEPROMs here, which each emit data lines, and those data lines effectively become the control lines going out to the various aspects of the computer. The input here is, first of all, this counter right here, which is effectively the step counter. The step counter controls the lower 3 bits of the EEPROM's address lines, and both of them. And then the next 4 bits of the EEPROM's address lines are actually the instruction register, which sets the, basically when you load the instruction register with an instruction, that instruction then activates the various address lines within this EEPROM, which in turn activate the right control lines. So the combination of the step counter and the instruction register lines should identify exactly which control line should be activated at any given time. There's 2 more things that he does. Is since he has 2 EEPROMs, he also has to identify which EEPROM is being basically used in any given position, rather than programming an EEPROM to be specific to a particular position. Both EEPROMs are programmed identically, and we just use an address line to identify which EEPROM it actually pertains to, so that when a given combination of counter and instruction register are applied to both of them, the additional address line would just tell this EEPROM to activate one set of lines, while this other EEPROM to activate a different set of lines. And then finally, there is one address line, the A10 address line here, that is unused and basically set to ground. So potentially this A10, is an opportunity for expansion, but as I would like to have more expansion than that. The other kind of important aspect here is how the step counter interacts with the reset. What the step counter is doing, obviously it's getting its clock signal coming in, the inverse clock. And if you want to know why it was the inverse clock, I will refer you back to Ben Eder's original video on why he's using an inverse clock here. So when the inverse clock signal comes in, obviously this counter will step through the various values here in the binary. However, we're using this 74LS138 to kind of do a 3 to 8 mapping, so that when this 3-bit binary number, whatever value it is, will activate a given line coming out of this 74LS138. And when we get to the 5th line, this is 5 line, which is actually the 6th line, since we're doing zero-based counting here. It basically gets fed into these NAND gates, which then in turn hit the reset line on the counter. So when we get to the 6th line, this counter is automatically reset to 0, which it's convenient. One of the things that you cannot do is reset the counter yourself. Let's just say you had a 3-step instruction that you're working through. You have to actually work through all of the 3 steps before you get to or the 5 steps before you get to this reset line on the 6th step that resets the counter, which in some ways represents some waste in terms of instruction time within the computer. So that it's a possibility for improvement too. It's something that even Ben Eder calls out in his design. The other kind of important element here, and I kind of want to call this out because it becomes an important facet when you start mapping out the overall design of your computer, is the fact that we are using inverters here. A lot of the units, the various units that you add to the breadboard computer, their control lines, they're kind of expecting an inverted control line. So when it goes low, whatever action that you wanted that unit to take is when it hits, as opposed to high. However, given the way that we've set up these EEPROMs and the fact that they all feed into LEDs, the EEPROMs are programmed such that when a given bit or line is 1, that's our intention to activate it. And so if the unit is actually active on low, you have to put this inverter in. One of the things that consideration is suddenly you need a lot of inverters, because a lot of things are actually active low rather than active high. And one of the things that Ben Eder did in his original design is put the inverters by the EEPROMs. I correct myself. He put his the inverters by the LEDs. As you make this larger, and you need more inverters, that becomes a unworkable design. I'll show you how I work through that in my design coming up. But I just wanted to point that out. Now, I'm not saying the need for inverters go away. In fact, they're still there. But you kind of have to rethink how you place them as you add more and more control lines to the breadboard computer. So, given this design, the question then is, what are options for expanding that? Well, one way to expand it would be, if you take a look at the 28C16 EEPROM right here. You could just simply add more of them, and here's kind of the pin layout. And if you add more of them, add one more, you have 8 more control lines. The problem is, as I pointed out, is we only have one more address line, and so if I have a goal to expand more address lines so that I can have a richer instruction set as I expand the memory and add more control flags, adding more of these EEPROMs just kind of simply will not work. And so another option would be to add some 74 LS138s. My data sheet here is for an HDT 138. I just found this a better kind of layout. The logic is exactly the same. It's just that the chip, the specific electrical characteristics of the chip is slightly different than the LS that we use in the Ben Eater design. But nonetheless, this still works for explaining what I'm trying to explain. So if you look at the LS138, the way it works is you have these 3 address lines coming into it, and depending on the value on that address line, it will make one of the output pins low. And if you can look at the truth table here, when all of the address lines are low here, then the Y0 output is low. And then when the address line, you have a high on A0 and low everywhere else, then the first one is low, and so on and so on. And basically, this is called a 3 to 8 multiplexer. It basically turns a 3-bit binary number into one of 8 outputs being active. Now, the challenge with this, well, first of all, how you would use it. The way you would use it is, rather than having 3 of these address lines going straight to a control line, you'd have 3 of these address lines feed into a 138, and then basically you turn those 3 address lines into 8 control lines. And rather than having one active, the specific combination of those address lines would turn into one of 8 of those control lines actually being active. And so, that's one way to expand that. One of the problems with using an LS138 is that they're active low. That is, the output is low. And so if our design paradigm was to have the output of these EEPROMs be high so that we can activate the LEDs and what have you, you immediately have kind of a conflict there. You have a choice. You can put every one of these output lines through an inverter just so you can get the LED high. But that becomes really cumbersome. Fortunately, there is a solution to that, and that is to use a 238 rather than a 138. And the difference between the two is that a 238 is active high on the output pins rather than active low. And so that works much better with the design. And so, that is certainly an option for expanding the Ben Eater's control logic, is just to replace some of the 3 of these address lines and pipe them into a 238 in order to expand them to 8. On its own, that doesn't satisfy all of my design goals because it doesn't add more address lines to the input to allow me richer instruction sets and so on. And so, but it is an option to consider. Now, one of the key characteristics with this option that you really have to keep in mind is, given the fact that this 238 maps a 3-bit binary number to a singular output line being active, you can't combine any of these output lines in the control logic. That is, only one of these can be active at any given time. Furthermore, the Y0 line, like if the address lines are all 0, which is what they're going to be most of the time, this Y0 line is always going to be active. And you don't really want that, right? You're not saying there is no component in the SAP-1 that is always on. And so really you can't use the Y0 line to be a control line. It just has no connection. So what you get out of this is in reality 7 control lines that are active high that you can't combine with other things. That's a design consideration that you design around. It doesn't prevent this from being useful. But on its own, it's not a complete solution to the design goals I have because it doesn't add more address lines. So the solution to adding more address lines would be then to use a different kind of EEPROM, specifically using the 28C256 EEPROM, which is very similar to the 28C16 EEPROM, but plainly, it uses more address lines. In fact, it goes up to 15 address lines from A0 to A14. It has more pins as a result, but it has the more address lines that I desire. Everything else about this chip is actually identical to the 28C16, except it has more pins and thus more address lines. It has the same inputs, it's used in the same way, has the same 8-bit output coming out. And so, this is a candidate. This is something that I certainly will consider. The solution that I actually ended up going with is to use a combination of the 28C256 and the 74LS238 in my design. Now, in reality, I ended up having to use the 74HCT238 because you actually can't purchase anymore the 74LS238, but you can purchase the 74HCT238. And HCT logic is more or less compatible with LS logic, so it ends up working. And so what I use in my design is the 28C256 in combination with the 74HCT238 to kind of give me a total of 12 control lines for each EEPROM and 238 pair that I put into the design. So let's get into the actual detailed electrical design here. Okay, here's the actual electrical design of what I ended up implementing for the expanded control logic. The things that you can immediately see is that I used 3 EEPROMs, which on their own would give me 24 control lines. But I pair each EEPROM with one of the 74HCT38s, which together are 12 control lines times 3, a total of 36 control lines. And then these control lines come out and they're all connected to an LED. I use some of the LED bar graphs in order for compactness rather than the 5mm LEDs that Ben Eater originally used, but it's still electrically the same concept. They're all connected to LEDs, so I can see which ones are active at any given time. And then I have also marked for the original control lines that were implemented in the Ben Eater design. They're all marked here and how I'm connecting them. Now, how they all get connected to a various component, that is, which one of these lines is which control line, that's a matter of basically choice, right? There's no specific reason why this line is out as opposed to this line being out, but other than just the way I kind of laid it out. Here are all the original inverters that I had to use for Ben Eater's control logic. And so what you see here is basically implementing all of the new EEPROM and 238 pairs, but still only implementing the original control lines in Ben Eater's design. With one exception. Here I have the B register out actually being implemented. So at least in this implementation, the B register is now a fully usable register. Now, there's another kind of important detail I want to kind of go through. I changed from Ben Eater's design. I still use a 74LS161 step counter. And this step counter, kind of like as it's designed, it counts through binary in order to activate exactly which step it's on, only using 3 bits, and we use the same kind of address line setup. However, it actually has a little bit more of a complex reset logic. And the way I do the reset logic, first of all, I I wanted to activate 8 steps. And the way I activate 8 steps is I let all 3 of these address lines, like be able to count through all 3 of these address lines. And when you get to the 4th output on this counter, because this is actually a 4-bit counter rather than a 3-bit counter, when this actually goes high, I have this map back into my reset logic. And I'll go over all the details of what's going on here soon. I just want to cover what are the inputs for the reset. So this maps back into my reset logic. And so basically when I count from 0 to 7, and the moment it ticks off at 8, it resets the counter forcibly. The other way to reset is actually through this control line here, which I call step counter reset. And so this control line, which is D7 on the left bank, EEPROM, just goes back also into the reset logic in order to either activate the reset or not. So what that means is this the step counter can be reset by either counting all the way to step 8, or the microcode itself activating this control line, which will reset the step counter. Now what's going on here is given the fact that the inputs to these resets are now going to be active high rather than active low in original Bend design, I could use basically OR gates in order to kind of bring in all the various inputs to reset them, because they're all active high. When this line is high, that means I want to reset. When this line is high, I want to reset. And then those OR gates will OR these inputs together and then ultimately get inverted because the step counter is an active low on the reset. So this inverter would just invert it. Now on the other end, the manual reset, because of this logic, the manual reset logic actually becomes much simpler. Rather than using the NAND gates as Bend originally used, I can now just use the simple inverter. I set up the reset switch so that it is normally low, and when you press the button, it goes high. I have the first inverter produce the inverted clear logic, which goes out to the rest of the computer, and then the second inverter is now again active high as it originally was, and I pull the active high reset logic off of there and send that off to the rest of the computer, and that feeds into these OR logics. So there are 3 possible inputs that could reset the step counter. Either the step counter itself reaching to the point to step 8, or the microcode resetting the step logic by activating this control line, or the user, you or me, pressing the resets button to reset the step counter. So this is the overall design. It is, and overall, it's very similar to Bend original design, with the important changes of adding more control lines by adding more EEPROM and 238 pairs, and then kind of changing how the step counter works so that I could have more steps. Okay. Now I want to kind of go over how I laid out this control logic and how I implemented an extended instruction set using the expanded capabilities of the control logic system I designed. What you see here is kind of a simple mapping of how any given instruction code and step maps to which control lines are supposed to be active at any given time. In Bend original video, he has a similar graph that he shows that he hand wrote. Here I made it in a spreadsheet, a Google sheet, just because I don't have his neat handwriting. But still, it's the same concept. It shows you for any given combination of instruction code, step, or flag, what control logic line should be active at any given time. Similar to Bend original design, we have the fetch step, which is true, the first 2 steps for every single instruction on the computer. The fetch step first reads the program counter into the address register and then loads a memory. The second step loads the memory address into the instruction register for the next, to figure out what's going to happen next. The rest of these things up until the JZ are the original instructions that Bend originally implemented in his design, but overlaid on top of my design for the control logic. Now, the way I have this laid out is you'll see I have kind of like 3 areas for the EEPROM and 238 pairs to kind of indicate what control lines they are. And the control lines that are activated by the EEPROM directly, I made yellow just to kind of make them clear. And the control lines that are activated by the 238, I made purple. Now, as you recall from when I talking about the implications of using a 238, for any given step, for any given bank of 238, only one control line can be active at a time. Now, a control line from two different 238s could be active at the same time, but within the same 238, only one control line can be active. And so I made it purple in the in this diagram just to help me visualize, to make sure that I was doing things right. And then I laid that out for each bank, the left bank, middle bank, and right bank of the EEPROM and 238 pair, what I'm going to be what each pin and control line was going to be used for activating. The design I have here is totally arbitrary. If you do this, you can use your own design. I try to organize it such that all of the register ins and all the register outs were on two different 238s. The reason being is you're never going to have more than one out active at the same time. So having all the outs on the same 238 seemed to make sense. And similarly, same thing with the ins. While it is true you could have multiple ins active at a given time because they're not writing to the bus, they're reading from the bus. For the most part, I didn't see that happening in practice. So a lot of the register ins I put on the same 238. Other control lines, like having to do with the step counter reset and the subtract symbol, I put directly on EEPROM, as you can see here, and so on. And so given that layout, I went down and kind of indicated exactly which bit should be ones, and anything that's not marked here implies a 0. Also indicated what the address line should be for any given step. Of course, I used the same kind of paradigm that Ben Eater used, where you have ones to indicate on, zeros to off, and X's to indicate don't care. And that don't care ends up becoming pretty important when you program this, because you have to program all possible combinations of on or off for everything that's X here. So there you have it in the design. You can see I added a few more instructions that I thought might be useful. This does not yet use any of the new modules that I may have added to the computer. It's just like there was about 5 more extra instructions in the instruction space in the 16-bit design, 8-bit design with a 4-bit address register. And so I just made some up. One of the interesting ones I made was this X8 instruction. It's not a practical instruction, but it was just intended to kind of demonstrate what you could do with 8 instruction steps. And basically what I'm doing is I take a number that's in the A register and I multiply it by times 8, which really means adding it to itself 3 times over. And if you look at the instructions here, that's exactly what's happening. First, I take the value out of the out of the A register and put it into the B register, and then I add, to activate the add step, which brings it, the sum out and bring it back into A, and activating the flag. After doing that add, I immediately check whether the carry flag was set or not. If the carry flag was set, that means I can't really add anymore. This is an 8-bit computer. You can't get numbers bigger than 255. So I bail. And basically, if the carry flag is set, set the step recounter and we're done, right? But if it's not set, basically I load the what's currently in the A value, which is in the first kind of iteration is basically A times 2, and load it back into B to add it back to the A register. Once again, after adding, I check to see if the carry flag is set, and if it is, I bail out of this step or instruction. If it's not, I add it one more time. And in that process, basically what I've done is I multiplied whatever was in the A register by 8. Thought that was interesting. Like I said, this is not a practical instruction, but it does demonstrate, what you could do with more steps in the step register or step counter. Okay, here is my design fully built. Not powered right now, but you can see it's all together, and you can see how my EEPROM and 238 pairs being in place, all the wires coming over to LEDs and then going out to the various components on the board to control them. You can see I used bar graph LEDs. I just found that to be more compact in the 5mm versions. Here are the two inverters that I used to convert the signals. These are actually the original two inverters that Ben Eater had in his design. I just changed the layout some, given everything. You'll notice my flags register is a little bit more complex. That's due to another project I've already completed. I'll be talking about it in a different video, so you can ignore it for right now. But the key part is the various EEPROMs, the step counter, and the bar graphs is what are the significant changes we're talking about here. Now, some tips on if you're going to implement this, some tips I have for implementing it. If you're going to do like me and you're going to start from the point of where you had the Ben Eater's original design fully implemented and you say, now I want to upgrade it, I found it far easier just to rip out all the original control lines rather than trying to reuse them. The reason being is given whatever new layout that you use for where the control lines are, it's just going to be different, and trying to reuse the lines just proved to be hard. I did try to initially, and it got confusing which line was which, so just ripping them all out and just starting over again proved to be the best solution. And the way to start over again is first implement or put into place the EEPROMs and all the address lines. I did the address lines here in purple just to keep that clear, and then implement all of these lines or put in place all of these lines that take the output of the EEPROM, either the data output or the 238's outputs, and wire them to the relevant LED that should be lit for each one. So since there are 36 of these lines, 36 of these LEDs get lit. Now we're not going to use them all because initially if we only implement Ben Eater's original design, there's only 16, or actually 17 with the B register out, 17 control lines that I actually need. But having them all wired initially just makes things easier later. And once you get those wired, then wiring each of the control lines into place proved to be easier. The other thing to point out that I already mentioned is these bar graphs just work better than LEDs. Also, when you make these wires come across, if you can kind of notice a little that it's elevated above the board rather than trying to be on the board, that just made things easier. And then when I bundled it together, I just use another piece of wire that I just wrap it around to keep it bundled together for neat purposes. It may not look the best, but I found it easier to do that than try to make things perfectly neat. And then one of the things I also found important is to orient the chips such that you're cognizant of what lines are coming out of it. And so these are all left pointing, the EEPROMs, because all the data lines kind of come out here. You'll notice how the three data lines that feed the 238 are actually on the bottom of the chip, so I feed the 238's inputs here, and that means their outputs are all on the same side of the outputs of the EEPROM that I actually do use, so these yellow sides, so that works out. But where that becomes important is actually right here, and this is the step counter, the 161, and the side of the step counter that has basically the output lines that we'd be using is on this side. Notice that I have this chip in reverse. And the reason why I put it on this side is because I didn't want to wire over the step counter chip in order to feed these address lines down here. And so by orienting like this, the wiring just became easier. The outputs of the step counter go straight into the inputs of the 238, and then I pull from that to feed the address lines of the EEPROMs. And in the end, things ended up being neater. And it worked out better, so kind of like that. Okay, let's go ahead and burn the EEPROMs with microcode that will enable what I just showed you. Now, in the original Ben Eater project, you actually implemented a EEPROM burner yourself using a Arduino Nano, some chips, and a specific wiring to be able to wire to the 28C16 EEPROM, so that you can burn a desired pattern onto it. In fact, you actually burned the Arduino with some logic that actually went through and figured out exactly what should be burned onto any particular address in the 28C16. Now, for this design, you could extend this burner by adding more address lines and then updating the code that you use with the Arduino. And it certainly is possible. But, at some point, it becomes impractical to use something like this to burn EEPROMs when there are so much easier solutions. Specifically, one easiest solution is to use an EEPROM burner. And here I have a Mini Pro. This is a fairly common EEPROM burner. You can find them on eBay for fairly cheap. And in fact, I think it's the same one that Ben Eater uses in his second series of breadboard computers that he uses. And so you can use this to burn an EEPROM. But what you do have to do is generate a file that contains basically the binary image that you want to burn onto the EEPROM. So let's go through and do that. Okay, so what you have here is basically a code that I wrote to generate the EEPROM file, the binary image that you need to generate. And what you have in it is it's fairly straightforward at a high level. Basically, I have this object here called microcode that generates the microcode. And then all I do is I iterate through from 0 through the top address in the EEPROM, figure out what the actual byte of that address should be burned to, and then write out the file. Right? And then it's that file that then ends up being used to generate by the EEPROM burner in order to generate the image onto the EEPROM. Now, I'm not going to go over this program line by line, but I'm going to highlight some important parts of it. First of all, how does this microcode object, how does it construct the actual image? If we go back to its constructor, you see something it's doing here. I'm iterating through basically each command. I'm going through each command, and I'm telling basically the object to set the bits of that command, where I tell what's the instruction address and what the step count, and then what are the control lines that should be activated. So for the first step of loading the A register from memory, the first step is actually to take the address register and set it to its in control line, and the instruction register out. Basically, you're telling from the instruction register, telling the address register what memory address it should be loading. And you'll notice that what I have here is I have like two variables here that I OR together using the pipe command, which in Python ORs either side of it together. And this produces the actual binary or the bit image that gets set at this specific address combination. What's interesting about how this works is if you go look at how these variables are declared, here is the address register in variable, and you see it is actually a object that I call microbits. And I declare address register in. This microbits object takes three arguments, takes 3 arguments, basically what the binary image or what bit should be active in any, on which bank of EEPROMs. Basically the left bank, the middle bank, and the right bank. And the way I laid out my control lines, the address register in is this bit, or basically the Y1 on this 238 is what's active for the address register in. And so this models that. And then what happens is when I OR this together with the program counter out right here, what ends up getting produced is another microbits object that represents these two bit images actually ORed together. So this microbits class is a fairly straightforward class. It's simple, and it just makes that logic easier to kind of manage. It contains basically, if you go to its constructor, it contains 3 values, which is the left, middle, and right, which is the basically the bit image for the left, middle, right, and it implements an OR and an AND function to properly OR together these two objects together, ORing the left with the left, the middle with the middle, and so on. Same thing with AND. And then some logic that allows you to specify bits either by passing an integer or passing a string, which represents which control line should be on by using 1s or 0s. And bringing it all together, you then can easily identify what command you want, and for each step, what are the control lines that should be ORed together in order, or collectively active in order to make that step occur. And then one thing you will note, the last step on every single one of them is setting the step counter reset. So this is what sets the step counter back to 0. Now, I did implement what I'll call an extended set of commands. And here, I want to point out one that I implemented, which I talked about previously when I was showing you. Here, how I implement the x8, or a multiply times 8. If you go down here, you see it uses all steps, and you see the logic, what I talk about, how it actually gets put together, how I have, some steps, the carry flag is relevant, but in some other steps it's not. In the case where you don't specify the carry flag, what the set bit does is actually set these bits to both the carry flag being on and off. So, that implements the full logic, the default or the X concept that you saw in the previous scene. So, fairly straightforward to use. Let's go ahead and use it. To use it, basically you have to run the Python program. Just run it as is, and it will generate the file as a binary file. Then to use that file, you then need to connect your EEPROM burner to your computer. And then one by one, burn each of the EEPROMs that with that file that we generated. So put it in. I got this thing caught. There we go. Okay, put the EEPROM in the burner, and then we just run MiniPro. Where you specify what kind of EEPROM that you're actually burning it to and what file you want to burn it with. And it couldn't be simpler. There we go. We've burned the left bank. Put it back in place. One of the issues with this layout is that since I put my 238 right next to the EEPROM, when I pull it out, sometimes I pull out the 238. You just got to be careful about that. Middle bank. And then let's do the left bank. Right bank. That was the right bank. There we go. Everything is now programmed. And let's try out this computer. Let's try it out. Okay, now that we got the EEPROMs burned, let's go ahead and power this thing up and program it and demonstrate that it works. So I'll add my power connector. Obviously it comes up in a random state. So I'm going to put it in program mode, reset everything, and let's program it. Let's go ahead and use the new command that we actually created. By loading, let's just kind of do some freestyle programming here. Load into 0 a load immediate, which would be 0, 1, 1. And I'm going to load a value of 1 into A. So program that in. And then we're going to, on the next one, we're just going to output that directly to the display, so you can see that we in fact loaded what we started with. And on the third step, or second address, but it's the third step, we're going to use the x8 command, which I have programmed to be 1, 0, 1, 1 is x8. So this will multiply the contents of A times 8. And then on the next step, address line 3, let's output whatever result we have right there. Great. Address line 4, let's just do it again. Let's do x8 again, just for the fun of it. So 1 0 1 1 0 1 1 is the instruction code I programmed for x8. And then line 5, we're going to output it again. And then 6, let's just go ahead and halt on this one, just to see that it worked. Okay, let's reset this and let's run it. See what works. We get the 1 in the register, and you can see multiply times 8, and you can see this this register kind of moving over as we run it. So let's reset that. Watch the register. You see kind of slide over as the multiply 8 instruction occurs, and so on. So there you have it. The extended control logic in place with some interesting new commands. But more importantly, the ability to add more modules, one of which you actually see right here that I have already implemented. I'll be talking about that in another video. But that's the goal here, is being able to add more modules and being able to control them and having the infrastructure in place to be able to do that. So hope you enjoyed this video. Put any comments or questions you have down in the comments below. I'll be happy to get back to you. And more importantly, if you end up implementing this, I'd love to hear about it. Until the next video,